you all on behalf of Akal University in today's expert lecture on nanotechnology, future for sustainable world. As in the month of April and May of this year, many parts of the world, particularly India and Pakistan, are experiencing heat waves, and climate change is commonly cited as the cause of these heat waves. In addition to heat waves, another issue we are dealing with is the rise in energy demand. In order to address energy issues and environmental concerns, we need sustainable energy resources rather than traditional ones like fossil fuels. So this lecture will focus on the role of nanotechnology in the development of sustainable energy sources. So I warmly welcome you all in this webinar. So without taking your much time, I would like to request our Dr. BirBikram Singh to kindly introduce our today's expert to the audience. Sir.
Thank you very much, Dr. Ramandeep Kaur. So I again welcome today's speaker and would like to explore his credentials to the participants and all the students who are with us, not only from Akal University, Talwandi Sabo, but from different parts of the world, including India. So Dr. Gurpreet Singh, who did his master's from India, from Guru Nanak Dev University, Amritsar, then he did he joined project of University Grants Commission, and then he moved to University of Brescia, Italy, and he did his doctorate from that place, and afterwards he did his postdoctoral research at different institutes of international importance, and basically nowadays he's leading a research team related to advanced nanomaterials for solar energy conversion, and his research work is basically mainly focused on the strategic design, nanoengineering, and analysis of the structural properties relationship of various multifunctional nanomaterials for sustainable energy conversion, storage, environmental remediation, and biomedical discipline. And he has published a number of research papers in reputed research journals with high impact factor. And his work has been cited by more than 1,400 scientists across the world. And he has received several awards and fellowships, not only in India, but also abroad. And he's reviewing the manuscripts for more than 25 journals of international repute. And nowadays he's a topic editor of Journal Physical Chemistry and chief editor of Canadian Journal of Agriculture and Applied Sciences. And if there's a long list of his achievements, and he's very young researcher and material scientist. And I would like to explore that in today's deliberation, he would explore the future of sustainable world in the context of nanoengineering. And before inviting him, I would like to mention this thing that this nanoengineering is an emerging field, not only across the world, but also in India as well. And there are certain issues which will be addressed by Dr. Gurpreet related to the subject. And hopefully our students, whether they are pursuing their graduate or post-graduation, so they will benefit from his discourse related to the topic. And now I would like to invite Dr. Gurpreet Singh and welcome him again. And we are highly grateful for his presence among us. And hopefully all the students will listen him and make their notes and would love to ask some relevant questions related to the topic. So welcome, Dr. Gurpreet. So now you are invited and to share his ideas related to the topic. Dr. Gurpreet Singh.
Thank you, Professor BirBikram Singh, for the nice introduction. So I'm going to share my screen. And I'm sorry if my voice is not good because I got fever.
Your voice is very nice, Dr. Gurpreet.
Yeah,
please
actually I got fever last night. So, anyways. Shall we start? Hello?
Yes, Gurpreet, start the
Go ahead, please.
First of all, I'm very thankful to the all participants and attending today's lecture. So today I'm going to talk about nanoengineering, and that is the future for the sustainable world. So I'm going to highlight how the nanotechnology or nanoengineering help to make our world more sustainable. So before going to talk about my research, so I would like to give you a brief introduction about my research journey, how I'm reached here, and what is my research journey. So basically, my research journey started with my master degree project that is under the Department of Science and Technology, Delhi. And while I was working at University, and I was working on the borosilicate glasses for shielding application. So in 2010, after completing my master's, I got the opportunity to become a research scientist at Punjab University, Chandigarh. So during that, again, I worked on the chalcogenide glasses for the information storage technology. So while working on amorphous materials, so I realized my passion toward nano materials. So therefore, in 2011, I moved to Italy as a visiting researcher. And after working 4 months over there as a visiting researcher, so we developed unique material of metal oxide metal oxide semiconductors. And in 2012, I got awarded with a full-time PhD fellowship. So, and during my PhD, I work on the application of the low-dimensional carbon materials like carbon nanotube, graphene nanoribbons, and their application in the solar cell and printable and wearable electronics. And during my PhD, I was visited other universities as a PhD exchange students, and over there, I have developed the metal-free organic dyes for the solar cell application. So in 2014, I completed my PhD, and I was get the chance to work for the Italy's National Research Lab, in India, like NPL. So similarly in Italy we have national research labs. So I worked 1 year over there as a postdoc, and during that I expand my research direction toward the clean fuel. And during that period, I visited to INRS, Canada. And when I visited INRS, we solved one big problem at INRS related to the solar cell applications, like especially third generation quantum dot sensitized solar cell. So after completing my 1 year postdoc at National Research Lab of Italy, so I moved permanently to Canada under the joint postdoc of University of Electronics, Science and Technology and China, as well as with Canada. So while working on these different technology, exploring my material in the different application part, as you can see, like in clean fuel, space technology, as well as then the solar third generation solar cells. Due to my achievement, I was promoted to a group leader in 2017, and since then I'm responsible for the Mytek Global Link program. So this is really very exciting program for the student from the developing countries like India. So every year we hire students like for 12-week program, internship program under this Mytek Global Link program. So in this, the government of Canada will pay you for 12-week fellowships, and during this you will have the opportunity to work with us. So after that one, you will complete your graduation, and then you are also welcome to join our group as a PhD student. So this is one of the best program, and if you guys need more detail about this program, you can reach me either by email or by LinkedIn, whatever the resources you have. So while working as a group leader, so further I expand my research direction toward the solar window, precision agriculture, waste management, batteries, and biomedical application. So during this, I was also a guest editor for the Molecule Journal. And in 2001, I came in touch with Dr. Dhinsa, and we started I started my visiting researcher position at Akal University. So right now we are going to develop research laboratory, nanotechnology research laboratory, and that I'm going to reveal at the end of this talk. And in addition to that, as I mentioned, as Dr. BirBikram mentioned, that I'm also a chief editor at Canadian Journal of Agriculture and Applied Sciences, and I'm also a co-instructor at the Simon Fraser University in British Columbia, Canada. So this is the brief overview about my research journey. So during this research journey, I would like to share one thing that in each phase of my transition from one phase to second phase, my professor, my teachers helped me a lot, and it's all because of my teacher what I am right now. So basically, if I talk about my research at INRS, and so basically our research is focused on the two topics. One is fundamental and second is the applied. In the fundamental part, we are trying to understand what happened inside the materials at the nanoscale dimensions. And we try to engineer its structural optical property by changing its shape, size, composition. And in the applied phase, we use that fundamental knowledge or specially engineered materials in a different application like surface science, organic electronics, biomedical, energy, environmental, and aerospace engineering. So the motivation behind this research is the sustainability development goals. So as we know that United Nations is doing considerable effort to achieve its sustainability development goal by addressing these 17 goals, so-called sustainability development goal. So as you can see that I highlighted energy in my title. It's because I and other scientists believe that by addressing the energy challenge, we can directly and indirectly solve several other challenges of the sustainability development goal. For example, good health and well-being, clean water and sanitation, and affordable and clean energy, sustainable city, climate action change, and life online. So there are, like, by addressing one challenge, we can contribute to so many other challenges. So now, what is this energy challenge? So basically, as you can see in this graph, still our main energy sources is the fossil fuels, right? So based on the current data, so still we are using our 80 to 85% of our energy from the fossil fuel, and that causing its rapid depletion because the fossil fuel are the finite source of the energy. And second is the environmental pollution, and that ultimately leading to the global warming. So based on the recent report, it shows that world's energy consumption will grow by 28% near future. So that's a huge, and we are already like this growing energy is depend on is increasing population. So as you can see that our population is increased very exponentially in after 18th century. Before it was very less population, but now it's growing very fastly. So this growing population demands more and more energy. And as I mentioned before that this energy comes from the fossil fuel. So this means higher the population, higher will be the energy demand, and that energy comes from the fossil fuel. And this means that we are creating more and more pollution, and that pollution, as you can see that we are increasing the CO2 level. So as you can see that in 1 century, the growth was only 4. And later on in the next century is 25. And very recently, just in short period of time, so we have 12%. So it's increasing very fastly. So we scientists, we have to think about this. And as you know that we scientists are not able to control the population because it's a more political agenda. So therefore, we scientists can work on a development of the technology that replace the fossil fuel. So there are so many renewable energy resources, but solar energy is considered as the most promising due to some reasons. So as you can see, this is the night view of our world, and you can see that like here, if we talk about South Africa, in the South Africa, only some portion of the area is these small dots is the light, and the rest of the part is like fully black. So this means that they don't have the enough amount of energy to to survive. So somehow we are lucky that India has enough amount of energy. You can see that whole India is fully dark. Similarly, in China, some portion has enough energy, but other portion has very less. And similarly, if we go to Australia, and only on the in the near to the sea area, we have some portion of light, but rest very less. But if we look at the daytime overview of this world, so you can see that where we need more energy, that area has high sunlight. So this means, for example, if we compare South Africa day and night, you can see that exactly in the same area where we don't have the energy, we have enough energy. So solar energy could be the one possible way to tackle this energy challenge. It's not only just its availability, but another thing is that it's available free of cost. We have to pay nothing to get the solar energy. And second, the amount of the solar energy that reaches on the surface of the earth in 1 hour is enough to fulfill 1 year energy demand. So let me give you one quantitative example. So for the production of 20 terawatt of the power, we need to cover only 0.16% of Earth's land that are shown in the red squares with 10% efficient 10% efficient solar cell. So this highlights that the solar energy has a huge potential to tackle the energy challenge. But when we see the contribution of the solar energy compared to the other renewable energy resources is very surprising. You can see it's very little compared to like wind or hydro. So the main reason behind this low contribution of the solar energy, that the current technology that we adopted to harvest the solar energy has high production cost. Second, the power conversion efficiency is low, and third is the limited operational stability. So these three factors depend on the what kind of material we used in the technology, what type of device architecture we used in the technology, and third is the integration, how we integrate our material inside the technology. So as a material scientist, I'm working on the nature of the material. So I'm working to design a smart material and smart device architecture to make this technology more efficient and affordable. So as you can see that during my research career, so I have developed a wide range of nano materials by exploring the nano engineering approach. So as you can see that I have like designed wide range of 0-dimensional quantum dot, 1-dimensional nanotubes, hybrid network of 1D and 2D and 2-dimensional nanoflakes. So in today's lecture, so I'm not able to cover all type of the material. So today we are going to focus more on the quantum dot, which is very hot topic in these days in material science. So to design nanomaterials, what is the guiding principle behind this? So basically, as I mentioned in the beginning of my slides, so basically we are trying to understand what happens inside the material when we shrink at its nanoscale dimensions. So at the nanoscale dimension, we realize that the surface of the material is significantly higher, like surface to volume ratio, we call it specific surface area, is significantly higher, and the surface of the material play a significant role to determine its functionality. So based on that, we develop a structural property relationship between the material and its property by tuning its morphology, composition, shape, and all these. So once we have understand the basic concept of the structural property relationship of the material, then we use that material as a building block in various applications. So let me little bit discuss about the quantum dot. So the quantum dot are the small size fluorescent nanocrystal within the range of 20 nanometer in diameter. So if we enlarge, this is the transmission electron microscopy image of the quantum dot. So, but when we enlarge it, you can see that each quantum dot is composed of billions of atoms, and they are perfectly aligned in a proper arrangement. So that's why we call most of the quantum dot are the single crystalline in nature. So let's discuss about the feature of the quantum dot. So now we discuss the structure of the quantum dot in the terms of the features. So basically what happened, so as we are decreasing the size of the material, so instead of its continuum and band gap, that continuum band gap is converted into the energy levels. So as we are shrinking the size of material toward the nanoscale, we are significantly change its internal structure, and because of that internal structure we obtain a different optoelectronic property. So in terms of, as you can see that, and this is the same material, so but in this what we did, we just changed the size of the quantum dot. So as you can see, by changing the size you can tune the color of the quantum dot. And also these quantum dot are solution processable, so we don't need a high-tech infrastructure to synthesize these quantum dot. And most interesting, these quantum dot has high absorption coefficient that we need for the solar cell application and as well as the other applications. And the most interesting part is the multiple exciton generations, and in which means the quantum dot absorb one photons and create a multi exciton with the single photons. And there is a possibility of the hot electron extraction before thermalization. So once we have a high energy photons, and then that photons passes through the quantum dot, there is a possibility that the electron excited from the valence band to high level of the conduction band, and that energy is further reused to excite the another electrons. So this is the basic information about the property of the quantum dots. But apart from these promising properties, so there are some issues. The issue is that, as we know that the quantum dot is small sized particles, and as I mentioned before, that when we shrink the material, the specific surface area is enhanced significantly. So similarly, in the case of quantum dot, we have high surface traps, and that surface traps act as a non-radiative recombination when we use this quantum dot in a device application. So due to that, we reduce operational stability of the device. Also, we promote non-radiative recombination because these traps act as a non-radiative recombination site, and also we reduce the PL intensity. So these are the main problem of the quantum dots. So what we are doing at INRS, we are trying to engineer its surface. So there are the two most commonly used approach. One is the ligand exchange, and second is the core shell. In the ligand exchange, we change the ligand of the quantum dots with the smaller ligands which have more proper dense packing, and that enhance somehow the surface property of the quantum dot. But we are more focusing on the core shell engineering. So what is this core shell engineering? So basically, in which the core of the quantum dot is passivated with the shell of a different material. And by designing core shell quantum dot, we are not only reducing the surface traps, but we also improving its a structural property relationship. And that is our basic concept to use these quantum dots, core shell quantum dot, in the energy applications. So as you can see that depending on the nature of the core and shell material, accordingly, we have a type 1, type 2, or reverse type 1, quasi type 2, or alloyed core shell, in which interface of the core and shell, we are introducing the alloyed layer. So depending on the nature of the material, accordingly, we can design the type of the quantum dots. So this core shell quantum dot, as I mentioned, reduce significantly the surface traps that enhances its chemical, thermal, and photophysical and chemical stability compared to the core quantum dot. And also the most interesting thing is that by tuning the core and shell material, and we can tune the band gap of the quantum dot. And also the core shell quantum dot has high quantum yield and better PL lifetime. So in our research group, we have a like big gallery of the different type of the quantum dot. As you can see that we are like able to design wide range of the quantum dots. So depending what our need, accordingly we design the quantum dots. So if I talk about the giant core shell quantum dot, in which we are like uh, doing a great job, and you can see in the giant core shell quantum dot, we have developed wide range of the quantum dot. And what is this giant? So basically in the giant core shell, so we have a very thick shell of the layer of the shell material. So this is the we call it giant core shell, and because of that a very thick shell, the property of the quantum dot is totally changed compared to the thin shell, and there is a possibility to formation of the quasi type 2, and in the quasi type 2 there is a spatial separation between the electron and the hole inside the quantum dot, and these quantum dot offer the excellent stability as well as better carrier dynamics, and it's easy to control its optoelectronic property. So what is our methodology to synthesize these different type of the quantum dots? So basically we are using wet chemical approach, and in wet chemical approach we have a different methods like inert vacuum line, in which we are synthesize the quantum dot in the inert environment, or we call it hot injection, and there is a heat up system, solvothermal, and ion exchange. So there are the different way to synthesize the quantum dot. So depending on our need, accordingly we choose the method to use synthesize the quantum dots. So once we synthesize the quantum dots, then we try to understand its carrier dynamics. What happened inside when we interact this quantum dot with the light photons. So once we have like the knowledge about the carrier dynamic inside the quantum dot, what happened inside the quantum dot, then based on that we use that quantum dot in a different application. So as you can see that with the absorption of the light photons, that and then they excite the electron, and that electron undergo trapping and retapping mechanism, and somehow it goes to the electron trap states, and from the trap state there is a possibility to radiative and non-radiative recombination. So basically we are trying to minimize these electron traps and the hole traps. So this is our main focus in terms of the quantum dots. So as you can see in this picture, so depending on the nature of the quantum dot, the injection of the electron from the quantum dot to the semiconductor materials, like if we talk about like Ti2, wide bandgap semiconductor material, so it's also changed. So you can see in the reverse bias, in the reverse type 1, we have a different mechanism for the electron injection, and instead of type 2, there is a different mechanism. So depending on the nature of the quantum dots, we can tune its carrier dynamics. So let's talk about the application of the specially designed quantum dot in a different technologies. For example, we are using this technology, these quantum dot in photovoltaic, clean fuel production, and environmental remediation, space technology, and biomedical engineering. So I'm not going to cover all the part of the quantum technology. I'm going to give a brief overview about each technology. So let's start with photovoltaic technology. And when we talk about the photovoltaic technology, the first thing in our mind is silicon solar cell. So no doubt the silicon solar cell is covered 90% of the PV market. But the main problem is that due to its high cost material, silicon, and complex production process and device architecture, because some of the light is reflected back from the silicon solar cell. So therefore, we scientists have to work on the two-way. Either we work on to optimize the existing technology by resolving these issues, or we come up with a new technology that can replace the silicon solar cell. So we are working on the second part, in which we are come up with a new technology which has a possibility to replace silicon solar cell. So that is the third generation excitonic solar cell. So in third generation excitonic solar cell, we are working on mainly dye-sensitized, perovskite, and quantum dot solar cell, because there are so many advantages of these solar cells. The first one is very easy to fabricate, and its manufacturing cost is much lower than the silicon solar cell. And the most importantly, the material that we used in these solar cell are eco-friendly, and they are very suitable to print on the flexible substrate, and they work under the diffuse light. So if we can use these solar cell in the indoor application, they perform excellently. So, but again, as this technology is still on the lab scale, and so we are trying to minimize the non-radiative recombination. So if we, as I mentioned, that we, in the case of quantum dots, we have a non-radiative recombination because of its surface trap. So these non-radiative recombinations that are shown by the dotted yellow lines, and because of these non-radiative recombination, we have overall performance of our third generation PV technology is less, and also the long-term stability is a main challenge. So at INRS, we are trying to minimize these non-radiative recombinations by exploring the core shell nanoengineering approach. So in the first phase, what we are trying to cover the core of the quantum dot with the shell of different material, like in this case is cadmium selenide is the core and cadmium sulfide is the shell. And by doing so, we, you can see, we move from 3% to 5%. And when we are engineering the interface of the core shell quantum dot, we further improve. And as you can see that by engineering the interface of core and shell material, and we significantly improve our efficiency from 3 to 5 and 5 to 7. And recently we obtained a new record in the power conversion efficiency. So in addition to that, we also obtain a pretty decent long-term stability for these type of the quantum dots solar cells. And but still we are struggling to further improve its power conversion efficiency as well as long-term stability. So in the third generation photovoltaic technology, we also work on the dye-sensitized solar cell, in which we use the dye as a light harvester. But in this technology, instead of quantum dot, we are using dye. But the other problem is that in these type of the solar cell is the carrier transport is the main issue. So to improve that carrier transport, we use the hybrid photonodes, in which we mix our materials with the low dimensional carbon materials. And I'm very proud to announce that we are the first scientist during my PhD that actually demonstrated the mechanism behind this enhancement in the power conversion efficiency by using very small amount of the power conversion efficiency. So I continuously working in this direction, and with the help of my team, and we also improve the long-term stability by 22%. And because of these achievements, we are contacted by the two Canadian company to use this technology in their organic solar cell. So let's talk about the second technology, that is building integrated photovoltaic technology. As we know that our commercial buildings are responsible for the 40% of global energy consumption, and which is a huge number. So if we are able to replace our building energy consumption with our renewable energy resources, then we can significantly reduce the impact of the buildings on our energy challenge. So basically, the most important approach that we adopted to reduce this energy consumption from the building is the building integrated photovoltaic. So what is this? So basically, we integrate the photovoltaic technology during the building design. But in the current technology, there are some challenges. So first one is the high cost, second is the low performance, and third is the incomplete understanding of the building integrated design, technology design. And the fourth is the technical knowledge from the relevant professional and the stakeholder. So basically, still we are in the initial phase of this technology, but the main problem that we are struggling is the high cost and low performance. And at INRS, we are proposing to use a luminescent solar concentrated window. So what is this luminescent solar concentrated window? So basically, it's an organic matrix in which we embedded with the quantum dots, and that quantum dot called chromophores, and they absorb the light photons at one wavelength and re-emit the light photon at higher wavelength and concentrate the light at the edges of the LSE. So basically, instead of covering whole window with the solar panel, we just on the window we just put LSE, and on the edges of the LSE we just put a very thin solar cells. So like we are significantly reduce the cost of the photovoltaic solar cell. So basically, instead of putting bigger solar panel, we just put very thin solar panel. So by using this technology, we can significantly improve our building integrated photovoltaic technology. For this type of the solar window, we have to improve the stock shift, and this is the difference between the absorption and emission error. So we are trying to tune this stock shift by changing the property material of the core and shell quantum dots. So in our research group, and we have developed a near infrared lead cadmium sulfide quantum dot core shell, and by using that quantum dot, we obtain excellent results. And I hope you have a question in your mind. This lead is the toxic and cadmium is a toxic. So that's why in parallel we are working on the eco-friendly based quantum dot that called carbon dots, and by using that one right now we have obtained quite promising results. So this is the how we are using this LSE. So basically this is the whole LSE window, and when the light passes through this LSE window, so as I mentioned in previous slide, so it's the chromophore inside this window is try to concentrate the light on the edges, and where we put a PV cell, and instead of putting in the whole area, so we just put the PV cell on the here, and then that PV cell convert the concentrated light into the electrical power. So this is the approach that we are doing to improve the existing building integrated photovoltaic technology, and we are working on the solar window. So while working on the energy conversion, especially for the electrical power production, so I'm also working on the clean fuel production technology. And in the clean fuel production, we are working on the water splitting. So basically in the water splitting system, so our system absorb the light, then there is a separation between the carriers, and then that carriers passes through the external circuit, and then that external, and after that they on one contra electrode, they generate the hydrogen production where the water splitting occurs. So basically, for this type of the system, we need a minimum band gap of 1.8 electron volt, and mostly the beginning of the hydrogen production start by using Ti2 or zinc oxide. But as you can see that because of its like wide band gap, it's absorbed only in the UV region. So which is and we, as we know that in the UV portion in the solar spectrum, we have very little amount of the UV portion. So to minimize these problem, we are come up with the use of the concept of the quantum dot sensitization and explore the one-dimensional nanocrystals in the electron transport layer. So as you can see that by combining quantum dot sensitization concept and explore of the one-dimensional nanostructure in the electron transport layer, we obtain a pretty decent record in the photocurrent density, and that leading to generate a 156 milliliter per centimeter square per day amount of the hydrogen. And also we obtain a pretty decent long-term stability for these type of the technology. So let's talk about the third technology. And as we know that water is our is the main source to survive, and but unfortunately there are so many sources that pollute our water. You can see in this picture, so there are the different. So to purify or treat this wastewater, we are developing a technology. So no doubt there is a photocatalytic wastewater treatment technology already there. But the main problem in that technology is that one is low photocatalytic efficiency under the visible light, and the durability of its constituents material and state of art, and high cost of recovery process, because when we use our catalyst, photocatalyst in a slurry mode, so its extractions is a little bit expensive. So that's why we are not able to use this photocatalytic current technology at the larger scale. So at INRS, what we are developing a solid state hybrid heterojunction photocatalyst, in which we engineer the interface of the metal oxide and the light harvester material, and by using interface engineering approach, and we obtain a pretty decent removal rate of the contaminants from compared to the control device. And actually this technology we just started, and within short period of time we obtain promising results. So apart from these energy conversion and storage technology, so we also work on the biomedical engineering. So and due to limited time, I'm not explaining all. So actually we are also working on the cancer research, and which is the main problem in our world. And we are developing a probe in which we can detect the cancer at its earliest stage. So we are working in collaboration with our medical departments, and we are in this technology in the initial phase in the lab level. So right now we are testing at the in vitro level. So later on we will move toward the in vivo. So in addition to the cancer research, we are also working on the development of the nanothermometers that detect the temperature at the nanoscale dimensions. And for this one, we have developed dual emission core shell quantum dots. And what is this dual emission? So basically, we excite with one photon of one wavelength, and our quantum dot emit the photon of two different wavelengths. And by using this especially in design core shell quantum dots, we obtain excellent temperature dependency in the range of 100 80 to 300 Kelvin with thermal sensitivity of 1.22% per Kelvin, which is also a record for this type of the technology. So the conclusion of today's talk is that the advanced nano engineering of the semiconductor quantum dot offer a unique opportunity to improve the optoelectronic property of the core shell quantum dot, and that ultimately help us to develop a cost-effective and highly efficient technology for a sustainable world. So what was my aim to join this Akal University? So this is very exciting news for all our fellows that are pursuing their career at Akal University. So basically at Akal University, we are developing Akal Nanotechnology Research Lab. So we are in the second phase of this research lab. So basically in this research lab, my main aim to develop a setup that work on the unsustainable energy conversion and storage technology. And then we also work on the environmental remediation, biomedical engineering, and waste management. So in this research lab, Dr. Deans and other fellows from the chemistry as well as from the physics department. So basically, once I think because if I understand, if I have complete knowledge of the status, I think we already bought some instruments, and right now once we have some promising results from our project, we have plan to write a funding at the national as well as the international level. And then as we are growing more and more, and we have a potential collaborator all over the world, so and definitely I'm more than happy to be the part of this. And what will be the opportunity of this proposed research lab? So basically it's perfectly aligned with the Akal University and faculty vision, and if on the law little broader vision, and it's also aligned with the India and United Nations Sustainability Development Goal. And this lab has a strong funding opportunity, and the training, which is the main aim of this research lab. So I believe that once we are successfully build this lab, our fellows will have the opportunity to get the training in this lab, and then they will have new skills and about the technology, and that are highly demand all over the world. And then in this lab, we have planned to design the new strategy for the sustainable energy technology. And this will definitely boost the economy of Punjab as well as India. And in this research lab, we are very diverse. So in this research lab, we have material scientists, nanotechnologists, biologists, and chemists also. And I would like to thankful to my research team and Professor Federico Ruzzi and all the funding agency who supported us to pursue this research. And thank you for your kind attention. And if you have a question, you can ask me. Thank you.
Thank you so much, Dr. Gurpreet. So we are having few questions from our students. So
Yeah, sure.
one question is there: which nanoparticles are used for increasing the efficiency of solar cell?
Okay, thank you. This is a wonderful question. So basically, as I mentioned, that there are different type of the particles. So in my slide, as I showed you, that there are the different type of the nanoparticles, right? So in the today talk, I just focus on the one particle. So basically we are combining different type of the particles, but today I just focus only on the quantum dot. And for example, instead of quantum dot, we are also using one-dimensional nano rod, nano wires also. And other than that, we are using two-dimensional particles, like nano flakes, and the hybrid network of both of 1D and 2D. So to increase the efficiency, we try to understand what are the main problem inside the device. So once we have that knowledge, so based on that, we design the material. So as we are working on the nano materials, so there is no a particular material. So it's depend on the need of the technology. So if we talk about the solar cell, definitely quantum dot is the heart of the solar cell. So that's why we are using quantum dots in the solar cell application, because it has promising optoelectronic properties. And there are some other questions in the chat also.
Yes, sir.
Okay, and why nanoscale property of the material? Oh, that's very wonderful question. So basically, as I shown in my slide also, so basically when we shrink the material, when we reduce the size of the materials and we goes to the nanoscale, then the surface to volume ratio, we call it specific surface area, is significantly enhanced. And the surface of the material at the nanoscale dimension play a significant role to determine its functionality. So that's why when we have a particle at nanoscale dimensions, and also if I talk a little bit more about inside the material, so what happens? So the band gap of the material is totally changed. Instead of its continuum energy levels, it's converted into discrete energy levels, and that discrete energy levels is totally different. So if I give you one very common example, as you see the gold in the bulk, it's a shiny color, right? But at the nanoscale dimensions and the nanoparticle of the gold materials, it's red color. So this means that at the nanoscale dimensions, the property of the material is totally changed because of its surface to volume ratio, as well as internal changes inside the material.
Thank you so much, Dr. Gurpreet. So I have one question. So,
Yeah.
If we talk about photovoltaic materials,
Yeah.
the main property which we want is the band gap, accurate band gap. So can we have a bulk materials which can give us these optimum band gap instead of these nano materials?
Yeah, thank you for this wonderful question. Yeah, definitely the simple example is the silicon. So silicon give us the optimum band gap, and that's why silicon is used a lot in the PV technology. But the main thing is that for the for the silicon based PV technology, it's to synthesize a single crystalline silicon. It needs a lot of like energy, and ultimately we are working to save the energy. So this means that in the initial phase we put a lot of energy to synthesize these materials, and that energy comes from the fossil fuel. So ultimately we are creating more and more pollution. So and moreover, like if we talk about the developing country over there, the silicon, the development of the silicon is really very hard. For example, if we talk about the South Africa, over there, to build a silicon solar panel is not feasible. So that's why we scientists are working on the technology that's very easy to build. For example, in this the solar cell that I discussed with you, no doubt they are in the lab level, they are in the initial stage, but definitely they are much simpler, as well as very less cost. And other than that, the material that we used in these solar cell are eco-friendly, so there is nothing to worry about to dispose these solar cell after when they are no more working. So these are the main things that we can say that this technology has a huge potential. And if I give you a recent example, like right now, approximately in Canada, the silicon solar cell gave us $1 per watt, and whereas the like perovskite or other solar cell has a possibility to give at 0.1 cent. So there is a huge potential. Yeah, and another questions. Can this core shell is achieved to get? Yeah, definitely. This core shell will help us to enhance the band gap value of the material. So basically, if you like when there is an offset, so based on the in the core shell quantum dot, the actual band gap of this combined system is depend on the offset value of the difference between the offset value of the valence band and conduction band of the combined material. So depending on the material you're using, we can tune actual band gap. And there is another question, Ruben. You're welcome. And there is a potential risk associated with the nanotechnology. Yeah, definitely every technology has a risk, and there are main thing is that in the nanotechnology is the handling of the material. So at the nanoscale, no doubt right now we have like enough technology to understand more about the material at the nanoscale dimension, but still there is a limit, and we can't go beyond that limit, and that's why still we are in the phase that like we know at certain level about the nanomaterial, but still there is a lot uh, to to do go beyond that limit. So this is, I think, is the limit of the main risk, I would say, for the nanotechnology. What are type 1, type 2, and also quasi type 2? If you want, I can share with you my slides, so that will give you a better understanding. Okay. So basically, your question was what is type 1, type 2. So you can see that is depending on the nature of the shell material as well as the core. For example, in the type 1, the conduction band and valence band is below between the conduction and valence band of the shell material. So basically in the and this type 1, electron and holes like the carrier are confined inside the core material, and the shell is mainly passivating them, right? But in reverse type, it's different. So the carriers are like this, and the carrier delocalize in the shell region. So similarly in type 2, we have the band gap in one case is just below in between the valence band and conduction band. So it's different. So as you can see in this one, so in the conduction, this is the valence band of the shell material, and this is the conduction band. So in this case, this valence band is in between this one. But in this case, the both are inside the conduction and valence band. But in this case, there is one. And due to this, one carrier is confined inside the core region, and second partially delocalized in the shell region. And in the quasi type 2, basically in the quasi type 2, this difference is reduced. So mostly, and based on our experience, when we increase the shell thickness significantly, we have this quasi type 2 structure. So in this quasi type 2 structure, we have a better carrier separation. For example, the like hole is confined in the core, and the electron is delocalized in the shell, because as you see, there is a less offset potential. So this is the quasi type 2. And similarly, we have alloyed, in which we have interfacial layer between core and shell. So these are depending on the nature of material. So we have type 1, type 2. And also what is our application part, like where we would like to use our quantum dots. Accordingly, we design the quantum dot. If we need type 1, for example, in solar windows, we need type 1, but in solar cells, sometimes we need type 2 or quasi type. So it's depending on our need of the technology, we are design the quantum dot.
Thank you so much, Dr. Gurpreet. So I think there are no more questions. So thank you so much. So now I am here. So it is a great honor and privilege for me to propose the vote of thanks for today's webinar. First and foremost, I thank our expert, Dr. Gurpreet Singh, for this very informative talk. The lecture focuses on the role of nanotechnology to generate sustainable energy resources such as third generation photovoltaics and photocatalysis. Further, I extend my sincere thanks to our Honorable Vice Chancellor, Professor Gurpreet Singh, for his generous support. I thank the entire management of the university. I would like to thank the IT team for all the arrangements. And I would also like to thank Professor Sukhjeet Singh, Director IQAC, for inviting Dr. Gurpreet Singh and make this webinar possible. I also like to thank my fellow colleagues, and last but not the least, I would like to thank our dear students for being a wonderful audience. Once again, I thank all of you for your attention. And for leaving the webinar, I want to make an announcement. Please fill the feedback form, which is provided in the chat box, so that on the feedback, on the basis of feedback, we will issue the certificates of this webinar. And please fill your details very carefully in the feedback form. So thank you so much. Thank you, sir.
Lucky, do you have any question?
Yes, Gurpreet sir, I think और कोई सवाल नहीं है बच्चे ना.
ठीक है, कोई गल नहीं जी. But if anyone want to reach me, I forgot. I think my email.
Yes, we have shared feedback and there is one column for suggestions also. If
sure.
receive any kind of query, then I will email.
Yeah, sure. I'm more than happy to help our students.
Thank you very much for sparing time.
Yeah, welcome.
Thank you, sir. Thank you.
Thank you, everyone. It was nice to meet you.